Hi everyone, I'm Jonathan Bruneau. I'm an electrical engineer here at Google. I specifically design Chromebook motherboards, and today we're going to talk about schematics. And why would we talk about this? Chrome OS is just a browser and operating system, right? Well, the truth is, we make Chromebooks, and there's hardware, but more specifically, there are people who write firmware, and firmware people have to look at schematics and figure out where does the signal go and how does it get there. So I'm going to provide some tools today to help everyone kind of walk the schematic a little easier. So before I go into all the details, upper management has required that I refer to you to slido.com, #Chromium, and we're in Chromium room C for all your burning questions. Okay, so when you first look at a schematic, pretty intimidating. There's a lot of stuff going on. The key thing is don't panic. What matters is recognizing patterns, and once you know the patterns, you can start deciphering the circuit. And at the end of the day, all we care about is you look at one end, which is your source, and there's a whole bunch of exciting stuff that's happening, and then your signal goes to its final destination. And that is the only thing that matters. Okay, but before we get into any of the details, let's start with the basics. The life of a Chromebook, electrically speaking, starts with a battery. The schematic symbol looks like either one of these. It's definitely not a AAA, but you get the point. And our dear friend Benji decided that we would follow the flow of positive charge leaving the battery. We refer to that as the conventional current. Too bad, he was completely wrong, and the real direction is we follow the flow of negative charge, electrons, and we call that the electron flow. But at the end of the day, we're electrical engineers. We don't care if electrons or positive charge go A to B, B to A. We don't care. Your light bulb turns on. Great. So we picked the wrong way and we follow the conventional flow. Batteries in Chromebooks are usually denoted with a red wire for the positive terminal and a black wire for the negative terminal. And we refer to the negative terminal as ground. And that is our zero voltage point. And then we follow energy leaving the battery that way. This is an actual Chromebook battery. This was in an AMD Lenovo Chromebook. And you can see right there, we have our black wire and our red wire. So charge, you plug the battery into the motherboard and charge literally leaves the battery pack, hits your processor, and then comes back through the black wires into the pack. Or it goes to RAM and comes back through the black wires, or all these mystery chips that are on the motherboard that have no idea what they do. Well, electrons go there and they come back. So when you look at what happens to the battery, we have the battery pack, and then we literally plug it into the connector on the printed circuit board in the Chromebook. And so our schematic actually doesn't show a battery, it shows a box with a bunch of pins on it, and that represents the connector. So that's where life starts. And just to be clear here, the red wires of the battery pack on our schematic are going to be represented with bold lines. So the bold lines on our schematic connect to the red wires on the battery. And the black wires of the battery would go and connect to the ground on the bottom here of the schematic. Okay, now we have all this exciting text up here. This is actually a whole bunch of random information. So Aces Electronics makes this connector. Their part number is 51279 blah, blah, blah. It's a 10-pin connector in case you can't see that from the schematic symbol. And then for Google specifically, we have a Google part number, and that's a unique number we give to each schematic symbol in our schematic that is indexable into a database. And then we can look into the database and see all kinds of completely random information. The J14 here is what we call the reference designator. We'll talk about that in a second. And then, the actual schematic symbol. Okay, so reference designators. What does that mean? Well, each part in our schematics, we give a number. And the number allows us to correlate the real world with our schematic. So here we have J14, which is our connector, battery connector. And then on the right here, we have J14, and that is in the printed circuit board design tool. And then if you were to look at an, oh, too fast. If you were to look at an actual Chromebook, you would see, hey, there's the connector and there's J14. So we can now map from the real printed circuit board back to our schematic. And we use this a lot when we debug motherboards. And there's a whole bunch of common reference designators. You can forget most of these. I've highlighted some of the more common ones. A lot of these are self-explanatory. Capacitor is C, diode is D, etc. If you're looking at different schematics, some people get it wrong. Some people do it differently. I don't know if anyone gets docked any points. They just get looked at kind of funny. Okay, so now we understand we have a connector, and I'm putting in our schematic and expanding our view a little bit here. Now there's a bunch of wires and text. The text on each line we refer to as a net name. So every single connection in a Chromebook schematic has a name, and we refer to it by that name for the rest of the life of the design. You could see that our bold lines, which was connected to the red wires on the battery, have a slightly different name. We refer to those as power nets. And then lastly, there's a few numbers here, like 28 and 23. These are intersheet references because electrical engineers live in the Stone Age, and we still draw schematic on pages. And we print these schematics, and then we flip across the pages to follow signals from their source to their destination. So if you were to look at this signal here, EC, I2C, power, SDA, on page 23, it says, hey, I'm also on page 28. And if you flip to page 28, it says, hey, look, I'm on page 23, and I have a second instance of it on page 28. And lo and behold, there are two places on page 28 with this signal. So that's all those numbers are. For power nets, every company I've worked at has kind of different standards. I'll just talk about the ChromeOS one. The power nets always start with PP or PN, PP being a positive voltage and PN being a negative one. I've never seen PN before, so forget it. It doesn't exist. And then we have the voltage of that power line in millivolts. And if we don't really know what the voltage is or it varies, we'll just place that with VAR. And then after that, there's a whole bunch of text that explains the domain, blah, blah, blah. You can more or less ignore that. Here's an example. PP 5000 always. So it's a positive voltage. It's 5000 millivolts, also known as 5 volts. And ALW in this particular design refers to always on. Great. So now back to a schematic, we have PP VAR BAT. So this is positive voltage. It's a variable voltage, and it's the battery power domain. And this makes sense because if you look at the voltage of a battery as you charge and discharge it, it varies, right? So PP VAR BAT makes a lot of sense. Okay, now I expanded our schematic a little bit. You can see now there's a power rail here. It's a 3.3 volt H1 always on. H1 is our security chip. Okay, cool, great. What's these squiggly lines here? These are referred to as resistors, and their sole purpose in life is to slow down circuits by converting energy into heat. If we didn't have these, we would have just a lot of fun sparks in our Chromebook, which I would argue is an awesome product, but probably not the best way to make a computer. Okay, so there's a bunch of text along with the schematic symbol of a resistor. We see the reference designator starts with an R, and then we have the value of the resistor. So this is effectively a 5000 kilo ohm resistor. We have the tolerance. In this case, it's 1%. It's practically impossible to make an exactly 499 kilo ohm resistor. So we have an error. So this is plus or minus 1% off of the resistor value. The next number is 0201, and that is the package size in mils. Electrical engineers have a choice. They can use millimeters or a completely nonsensical unit called mils, which is 1,000th of an inch. And for some reason, the mil sticks around. So here we are with a resistor that is 2,000ths of an inch by 1,000th of an inch. And the last parameter is the wattage. It's how much heat can this resistor generate before it self-destructs. Typically, the package size implies the wattage, so a lot of the schematics just omit the wattage parameter outright. So we can owe all of our understanding of resistors to George Ohm, who is a genius and deserves a yellow halo. He discovered that the voltage that develops across the resistor is equal to the current across it times its resistance. And in this also, that the power, i.e. the heat generated by this resistor equals the voltage across the resistor times the current. So heat equals fire. Here's an example. Suppose we have a 5-volt battery and we have a 1 ohm resistor and an O201. You plug in the math, you figure out, okay, that's 5 amps across the circuit. And you plug in an hour for power and you get 25 watts. Now, I don't know if anyone of you had the pleasure of touching a 100-watt light bulb. 25 watts still is extremely painful and way over our O201 limit. So the resistor would self-destruct. Now, just by changing the value here, we can go to 100 kilo ohms, and you plug in the math, and your total power is 25 milliwatts, which is way below the 1/20th watt limit. So everything's hunky-dory. Now, there's a lot of interesting things that you can do with a resistor, and frankly, I forgot most of them. The only thing I use every day, and this is the most important, is the voltage divider. Given an input voltage and 2 resistors, you can get a predictable output voltage. And this is the equation. I will not derive it for you. Here's an example. 5 volts coming in through Vin hits a 2 kilo ohm and then a 1 kilo ohm. Do the math, and V out is 1.6 volts. Oops, too fast. Cool, great. Okay, that's resistors. So what's the 0 ohm? Why would you want a resistor with no resistance? Isn't the point of resistors to slow circuit down so we don't get sparks? Well, you're right, but printed circuit boards are fixed. We fabricate them and then we can't really change them. So as we're developing the circuit, we don't really have the ability to change where the copper on the printed circuit board can go. So suppose I wanted to cut this line here, I would have to pull out my X-Acto and use my X-Acto skills and frankly just cut myself a lot. It's not fun. So instead, we put a whole bunch of 0 ohm resistors, and then we can, with our solder iron, very easily remove it. And that allows us to connect and disconnect or rewire the printed circuit board altogether. So that's exactly why you'll see a 0 ohm. And a lot of times our 0 ohms will have the words DNS on them, which means, yeah, okay, I put it in the schematic, but when you make the circuit, don't actually put it on the printed circuit board. Other names for this are DNP, DNI. I've seen a star. It's not really a good standard here. Sorry. Okay. Making the schematic a little bigger here, we have these 2 little bar-looking things. These are capacitors, and the 2-word explanation of them is that they store electricity. We have the reference designator, starts with a C. The value is in farads. This is, again, the package size in mils. So this is 4,000th of a mil by 2,000th of a mil. This is the maximum voltage in 50 volts. And the temperature coefficient is something you can completely ignore. It's completely irrelevant. If you go over the rated voltage for the capacitor, it will explode. Okay. I'm just going to talk about the step response of a capacitor quickly here, because this ties into this presentation, also the one tomorrow, should you be interested in learning more about this. So the step response is basically, you have this setup where you have a voltage source, a resistor, and a capacitor. And when you turn on the circuit, when you plug in the battery, so to speak, the voltage will rise over time. And it's worth noting that the voltage rises over time and starts at 0 and gets to the battery voltage, in this case, 5 volts. And the current does the absolute inverse. So it starts at a very high current and then works its way down to 0 amps. Okay, that's all I'm going to say about that. All right, so now back to our schematic. If you look here, my God, we have this resistor, we have the capacitor, we have ourselves the low pass filter I just talked about. Cool, that's neat. Now what about this guy? What's that? This is a MOSFET. This is a type of transistor we use pretty much all over the design. There's different types. We stick mostly with MOSFETs. Okay, Each pin of the MOSFET has a name. This pin here is called the gate, and this is what controls the MOSFET and turns it on and off. This is the drain, and this is the source. The way that you can read what type of MOSFET it is by the symbol itself. So the arrow here pointing towards the center of the gate is referred to as an N-channel MOSFET, or N-FET, or NMOS, depending on which part of the country you're traveling. If the arrow were to point away from the gate, this would be a P-channel MOSFET. Now, these two lines connect together, and the connection here tells you where the source is. Let's see, yeah, I think that's all I have to say about that. Yeah, okay, so the reference designators for transistors is Q. You'll see a part number. This is an extremely common N-channel MOSFET. 60 volts is the maximum voltage you can have across the drain to the source before the part explodes. The 4 ohm is usually a cell sheet resistance. We'll talk about this in a second. This parameter is not super useful. This is the maximum amount of current that can go through the drain to source before the part explodes. It's worth noting here that our amazing CAD tools don't really do case, so everything is in capital. So you have to use a little bit of judgment here and realize that 300 megaamps is a huge amount of energy, and this isn't actually a 300 milliamp. Sorry, if you could fix that problem, I'd love it. Okay, and the package here enters a whole world of different packages. I won't get into it. This is basically just the package itself. Again, if you exceed those parameters, things explode. Okay, so my 2-second description of how transistors work. There's a gate to source voltage here, and this is referred to as the resistance from drain to source, and this is the current entering the drain. Show by example. So if the voltage at the gate is 5 volt and the voltage at the source is 0.5 volts, my gate to source voltage is the difference between the two. So it's 5 volts minus 0.5, which is 4.5 last time I checked. So you can walk the graph and start at 4.5 volts, go up to the graph and across, and that will tell you the resistance, the RDS resistance of the MOSFET. In this case, it looks like 0.9, right? Okay. Now, if I change the gate and I say I do 2 volts, now my gate to source voltage is 1.5 volts. And on the graph, I do this and I'm off the charts. So I'm going to call this an extremely large value, 3 mega ohms. Turns out datasheets don't really provide this parameter. And unless you're doing something really specific, you don't particularly care. All you care about is that it's huge. And for all intents and purposes, that's good enough. But it's worth noting that in effect, what we have is a voltage controlled resistor. So let's see how this applies in practice. Suppose I have this circuit here, and I'm going to call this side the input and that side the output. So when I apply 0 volts on the input, I get a gate to source voltage that is 0 volts. So I'm going to call the RDS 3 mega ohms. What we have in effect here is a voltage divider, right? We have a resistor down here and we have a resistor up here. You plug in the math and you end up with V out equals to 1.74 volts. Okay, now if I apply 1.8 volts at the input, I get RDS of 4 ohms, a number I picked out of thin air. So again, applying the resistor divider math, you end up with 71 microvolts. So in effect, what in effect I've achieved here is that when I give 0 volts on my input, I get almost 1.8 volts out the output. And if I have 1.8 volts on the input, I get in effect 0 volts. This is an inverter. I can take a signal and invert it. And going back to our schematic, if I told you that there was a resistor here in the battery pack, you would see, aha, there is an inverter. We usually refer to this configuration as open drain, and we will name the nets accordingly with an underscore OD at the end for open drain. And by the way, this drain is the drain that we're referring to when we talk about open drain. Okay. Now I talked about MOSFETs, but what's this thing? That is referred to as the body diode. And before I can talk about body diodes, let's talk about diodes. Diodes are a device that let current go one way, but block it the other. So if I have a situation where I have 3.3 volts on the left and 1.8 volts on the right, the diode will turn on and let energy go through it. But if I have the reverse, the diode will block it. Okay, in the schematic, you'll see just like all the other parts, we have a bunch of text. This is the reference designator, starts with a D. This is the maximum forward current, the part number, the package, again, a whole world that we're not going to get into. This is the voltage drop. I'll talk about this in a second. And this is the amount, the reverse blocking voltage. This is wrong. I need to fix that. Is the amount of energy before that the diode can withstand before it blows up. And really, these two parameters are what make or break a diode. Okay, so let's talk about forward voltage really quickly. In a perfect world, diodes are perfect. And so they block and allow current without consuming any energy. But we don't live in the perfect world. So the diodes burns some of that energy off. And the way that it manifests itself is that the voltage, the diode will consume some of the voltage, right? So here's an example. Suppose I have this magic current source that can always source 1 milliamp. The way that you figure out what the forward voltage is, you grab your forward voltage versus forward current graph, and you look at 1 milliamp, you go across and down, and that tells you, okay, looks like the forward voltage is about 0.31 volts at 1 milliamp. So if I have a 5 volt source and I'm sucking down 1 milliamp, the forward voltage is 0.31 volts. So if I were to grab a multimeter and measure the other side of the diode, I would get 4.69 volts. Okay, in practice, let's see how this is useful. I have this circuit here. I have two inputs and an output. When I apply 3.3 volts on both my inputs, and my power source here is 3.3 volts, the energy is blocked by the diode. So my output will be mostly fed by this power supply and this resistor going out. So the output will be 3.3 volts. All right, put that in a handy chart. So now, if I make one of the inputs 0 volts right here, what happens is the top diode blocks, but the bottom one turns on. And what we get, we develop a forward voltage here, just like we talked about earlier. So the output would actually be the forward voltage. Put that in my handy chart. Now, if you do the reverse, you get the same thing. And if you both are 0, you get the same thing. You end up with this chart. Now, I'm not known to really write code, but if you were to write code here to say that if the voltage was greater than 2.7, we'd call it a 1. And if it was below 1, we'd call it 0. And you apply this to this table, you would get this logic table, which, as it turns out, is an AND gate. So this is the logical AND of A and B. And we use this all the time in Chromebooks. So this is an example of a 3-input AND gate, and one of the input is not stuffed. It's worth noting here that this particular signal has the underscore L at the end, and this is referred to as an active low. This is the kind of signal that is normally a logical 1, or in this case would be a 3.3 volts. And then when something exciting happens, it goes all the way to 0 volts. And we can combine them. So this is a open drain active low signal. So this is ODL. Okay, back to our body diode. It's just a diode like we've just talked about, but it's a really bad one. If you look at this, about 1.5 milliamps and come across, this is like a 2.2 volt forward drop, which is terrible. This is not a good diode, but we use it anyways. And here's a circuit that exploits this property. We have two resistors and our MOSFET. This is an N-channel MOSFET because the arrow is pointing towards the gate. The connection between the arrow and the pin here happens there, which tells us that's where the source is. So now we know where our gate, our drain, and our source are. Okay, I'm going to call the right side the input and the left side the output. So suppose I make my input 1.8 volts. The gate to source voltage is 0. So our resistance across this transistor is huge. Ironically, this is a voltage divider again, and I'll spare you the math, the basic high-level concept is that most of the energy for the output comes from this 3.3 volt rail across this resistor. So in effect, given 1.8 volts, we get a 3.3 volt output. Okay, so now if I change my input to 0 volts, the gate to source voltage is 1.8. And I will say that the transistor turns on with a resistance of 4 ohms. Okay, now we have a voltage divider again. I'll spare you the math. High-level idea is that most of the energy goes from the 3.3 volt rail and across the transistor to 0 volts, which means that this wire here is also 0 volts. Okay, what we have now in effect is a level shifter. If I give it 0 volts, I get 0. But if I give it 1.8, my output is now boosted to 3.3 volts. Neat. But this circuit has one more trick up its sleeve. Now, what if we switch the input and the output? In this case, if my input is 3.3 volts, this energy comes and hits the body diode of the MOSFET and is completely blocked. So the output is fed from the 1.8 volt input here across the resistor. So our output is 1.8 volt. Okay, this is where it gets really exciting. If I make my input here 0 volts, the diode will conduct, right? Because the energy comes from 1.8 across the resistor, across the diode, all the way to 0 volts. So the output is going to develop the forward voltage. Now this means that our gate to source voltage is increasing, which means that the resistance across the transistor is decreasing, which means that over time, as this continues to happen, the voltage across the transistor will be dominated by the voltage, by the IR drop created from that resistance. I did not say that right, but I think you get the point. All right. So over time, the gate to source voltage is increasing, which makes the resistance across the transistor continuously decrease. And you get in this really positive feedback until eventually your resistance is so small that the transistor is fully on. At that point, the voltage at the output is 0 volts. So in effect, when I give it 0 volts, the output is 0 volts. So this circuit is actually a bidirectional level shifter. Given A and B, I can either have A be the input or B be the input, and they both provide the level shifting functionality. Cool. And we use this circuit all the time because it's super cheap. You look at this schematic, pretty intimidating, but break it down. Oh, look, there's a bidirectional level shifter here, there's one here, and there's one there. And that's really what it is. Once you see that block, you don't have to think about it anymore. So given this schematic now and all the things that we know, we can start breaking it down. Right? This is our level shifter we just talked about. This is the inverter. This is the low pass filter. And this low pass filter is connected to then an inverter. This is a non-stuffed AND gate. This is also a level shifter. And this is also an AND gate. So really, at the end of the day, reading schematics is all about finding the patterns. We're not launching anything to space here. So Chromebooks are not rocket science. These schematics have been well defined and the patterns are well fixed and understood. So once you understand the patterns, you can start reading schematics. And if you have a question, that's when asking your local EE friend is always a great idea. I heard they accept payment in beer. And lastly, we've barely scratched the surface of all the cool stuff that you can discover and all the patterns you can learn from schematics. So tune in tomorrow, same bat channel, same bat time, and we'll talk more about this. Okay, time for questions. Let's see. Okay. I'll wait a minute or so for questions, and if there's nothing, then we'll call it a day. Okay, well, I guess I either did a great job or a terrible one. So I appreciate everyone's time here, and I hope that we learned a little bit more about how to read these seemingly scary schematics in a not so scary way. All right, if you want more of this, I'll be on tomorrow again at the same time, and we'll talk more about Chromebook schematics. Thank you, everyone.